Okay, thanks everyone. Thanks to you too. So today's talk is going to be about deep learning for speech recognition. Just a quick straw poll. How many of you have worked on speech recognition or are familiar with that? Okay, some of you. Okay, cool. So I can probably move. So what exactly is speech recognition? I think we all probably know this. We have a speech recognizer which understands speech and transcribes that to give what words are being spoken or have been spoken. So this is all good, right? This is something simple and we can do it. But there are some problems. And I want to show this little video if it works.
Daga, Alexa, wait, something's cooking in my kitchen by Daga on my Spotify. I can't find something's cooking in my kitchen by Daga on Spotify. Daga, Alexa,
Okay, so this was a longer video and I do not want to show the part where she gets frustrated, like really frustrated. So that's why I cut it. But, so you understand this part, right? We have accents in our voices. We have background noises in speech. So it's very difficult for machines to understand it. Humans are really good in understanding speech, but machines unfortunately are not. So before moving on to the deep learning side of things, I want to quickly talk about speech recognition in a traditional world. So what used to happen? Basically, you have this particular speech signal, and you convert that into some feature representation. And you have different kinds of models, like acoustic model, a pronunciation model, and language models. So the rationale behind each and every model is to model the speech which we get from our input into some sort of a decoder, and the rationale or the job of the decoder is to recognize what words are being spoken. So in a mathematical perspective, you are just maxing out or probably finding the max of the words, the probability of word that you think would be mapped to the speech signal, right? And this is probability of each and every model, just concatenating or multiplying these probabilities. So this is in a traditional world. What happens in a neural networks world is everything changes to neural networks. So we have the entire same pipeline, but instead of having Gaussian mixture models and n-gram language models, we now have neural language models, and we now have LSTMs and hidden Markov models instead of that. And we'll talk about this in more detail and one specific algorithm in much more detail in this talk. So moving on, what kind of data is a speech signal, right? So this is a one-dimensional signal, pretty simple. Typically speech is quantized in 8 bits or 16 bits, and it is 8,000 samples per second, right? So whenever you see a speech signal, it can be transformed into a vector of length 8,000 or 16,000 based on your sample, and each and every value in this vector would be a floating point number representing the value of that particular instant. How many of you, again a quick straw poll, how many of you have seen or heard of a spectrogram before? Okay, actually many of you, so that's pretty cool. Spectrogram is nothing but a representation of speech into something which we can quantify later for our neural networks. So basically there have been studies and people have modeled speech directly into words or tokens. But we've usually found out that if we convert speech into spectrograms, it's better in terms of analyzing that particular speech, and I'll tell you why. But before that, I just want to give you a quick background on what a spectrogram is. Whenever you see a speech signal, you can take a small slice of that, and inside that small slice, you see a smaller speech signal, and that smaller speech signal, you can do a Fourier transformation in that. So when you do a fast Fourier transformation, you're converting that into power versus frequency. So this particular graph for power and frequency can be quantified for a particular frame. And the particular frame is now a spectrogram for that particular instant, right? And you concatenate all these frames and it becomes a spectrogram for the entire speech. Now, people have done discrete concatenations as well as continuous concatenations. So that's a hyperparameter that you can tune. Mostly what I've done is to use a 20-second window and discretely just concatenated all of them. Now, whenever you have to do a modeling task, you have to consider that in a way that you have an input and an output, right? So the input here is your speech signal in some vectorized fashion, right? And the vectorized fashion comes from a spectrogram, right, like here. So you can see the speech signal has been quantified into a feature representation, and that feature representation can be in some way be denoted as this. Our objective is from this accurate mapping of feature representation, find out what are the words or what is the output, right? So instead of going through all these three different models, what we are trying to do is to have just one particular model and one particular probabilistic model which can go from speech signal and spectrogram to words or to the transcription of that. So it's end-to-end deep learning for speech recognition. But what are the challenges with this end-to-end approach? So there are some problems associated with this, and the problems are that X and Y, if you saw the last slide, the length of X and Y, which is the input and the output, are not same. So for example, if I give you a 20-second window, it might happen that it will turn to a particular token, but the next token can also be the same. So if I say hello pretty slowly, it's different than if I say hello pretty quickly, right? So the input and the output are different because the output is definitely hello for both these different speech signals, but the inputs are very different. Not only this, the ratio of the lengths are also different, so there's no way in which you can map the length of the input to the output. And there have been solutions in the industry and research in academia. People have used attention models to do this, and some people have also used like very specific speech recognition models called connectionist temporal classification. And in this talk, I'm going to talk about the second one, which is connectionist temporal classification. So for CTC, we have these four different components. The first one, okay, cool. The first one is an RNN, which is a recurrent neural network. What we are going to do is, because we need a way in which we can map the length of the input to some representation in the output, RNNs gives us a way to do that because the length of the input and the length of the output neurons will be the same for RNNs. So then after that, we can have a mapping from the output or the RNN output neurons to the actual output. And we're going to talk about this in detail again. But as for any other machine learning or deep learning algorithm, we're going to quantify and maximize the likelihood of that particular input that we give, and also find out what is the likely output for one given input, right? So this is a very high level, sort of like a diagram for what you can have in a CDC model. So going into each and every bit in detail, first one is an RNN encoded distribution. So I have a speech signal, and then I converted that into spectrogram. After that, I feed the spectrogram frame by frame into an RNN, and that can be any sort of RNN. Generally, people use an LSTM and even bidirectional LSTM because it gives you better results. But for now, let's say this is a vanilla RNN, right? And the output of this RNN is a bank of softmax neurons. So C is an intermediate representation from input to the output, and C denotes what is that particular character at the instant where the spectrogram is being tested. So, for example, if you see row number 2, and if you go on the 17th spot, you can say that this is the probability that this character would be a B given your input X, which is this particular thing in the spectrogram, right? So at each and every instant, you're finding what is the character. And the vocabulary set of these characters is limited in the sense that because these are characters, you'll always have something from A to Z, and then there are two special increments in this particular model, which are blank and space. I'll talk about blank and space in a few minutes. So when you have this set of characters, if you assume independence of each and every character, for example here, if I assume independence that something on t equals t minus 1 and something on t equals t would be different. If I assume that, I can say that it's the probability of finding a particular character is just the probability of the entire sequence, multiplication of the probabilities of the entire sequence, because you're assuming a naive independence assumption there. So, for example, if we take the example of something, let's say hello, the probability of that would be character 1 is H, 2 is H, and then character 15th is a blank, right? And the concatenation in a way that you have a multiplicative index here would be the probability of the entire speech. So just to give you an example how this mapping works. So see, you have an input like speech, and then there is a sequence of tokens. So what you do is you merge the repeats and squish down the blank. Blank here is represented by epsilon. So if you see hello world, it's just whenever there's two E's, they're just squishing it down. Whenever there are two L's, they're squishing it down. So what happens here is this. So whenever you find three H's, you squish them down to one H. So squeeze out your duplicates and remove the blanks. So here two L's, you squish it down to one, and then so on and so forth. Now, I was talking about why blank is important. Blank is important because we want the best obtainable spelling of a particular word, right? So if I had no blanks, I would squish down these three L's, and it would be H-E-L-O instead of H-E-L-L-O, right? So blank is one of the terms that's important here, just to have better spellings of the input that you want to have. Now with any sort of machine learning algorithm, if I give you the actual transcript or the actual label, and if I tell you to tune the hyperparameters to get the actual transcript, what you will do is to maximize the likelihood. Right? So we'll do the exact same thing here. We'll maximize the likelihood of the probabilities of a particular thing being in our testing or being in the label set. Or the label set is basically labels or the correct transcription of a particular speech signal. So here when I say log of p y star given x, x, it's basically telling you the probability or maximizing the likelihood that y is basically the correct transcription of that particular speech signal, and we want to maximize the likelihood of that. So how will we do that? We'll basically, whenever we get the speech signals, what we'll do is that we'll maximize the likelihood of that particular instant instead of going through the entire thing. So instant after instant. That's why we did like the 20 millisecond window. So Alex Graves and co-authors in 2006 came up with a very efficient solution, a dynamic programming solution to calculate this double additive here. And not only that, instead of calculating just the inner summation, they also came up with a way to calculate the gradients. So now there are off-the-shelf solutions of calculating the CTC loss. So if you go in PyTorch or TensorFlow, you can calculate the CTC loss just by calling that particular function. So you don't need to go through the entire thing that we just discussed. You can just call that particular function, calculate the loss. So again, we run in some problems here. We might think that having a mapping which squishes down the duplicates and takes the blank spaces off, like removes all of them, might be a good approach, but it usually outputs something like this, which kind of makes sense, but what exactly is Boston? Or what exactly is this? Can anyone tell me, what do you think of the third sentence? What should be the accurate transcription of that? Are there any tickets for the game? So this is like not close to that at all, right? And it makes sense because we say things in a different fashion. So whoever transcribed it or whoever said this must have said something in this range or in this fashion, something like that. So what is the solution here is going to different approaches. So you can do a modified beam search, you can do like prefix decoding, and for a lot of time, modified beam search was the pinnacle or the state of the art for this. But recently, or I would say not so recently because it's been some time. So within the past 5 years, we have understood that language models are really good in identifying context. So we're using language flow for augmentation here. So the language model solution is just to fuse the acoustic model, which we've just trained, into a language model. And it helps because it learns the grammar. So now you have that understanding of what exactly is a particular word. So you don't know, you would know, okay, that there are so many words in my vocabulary, and whatever I'm speaking is one of those words. So language model gives us a particular set of vocabulary. And it also expands on whatever terms we are speaking, right? So it gives you a perfect spelling, and it gives you a way to expand your vocabulary. So you will not get something like Anthony Lever down sky. Instead of that, you will get the actual thing, which is Anthony Lewandowski. So again, because we are including language models, so we have to retrain our model or change our likelihood statement. So likelihood statement changes. It was just this before, but now we have the language model augmentation. So we include a language model probability here. And in addition to that, we've seen that whenever you include a language model, you always tend to, penalize those words more which have longer spellings or which are longer in character count. So just to account for that, we have this particular bonus or penalty term, which gives a higher penalty to smaller words and a lower penalty to larger words or longer words. So what we've seen is we get better results. So instead of Boston, you get the actual Boston spelling. Instead of, I don't know what is that, but are there any N tickets to the game? We actually get, are there any tickets for the game, right? So we get better accuracy and better performance of our speech recognizer with the help of language model augmentation with the acoustic model. But there are some problems with whatever we have discussed. So these are good for things like if you have to publish a paper at some conference like Interspeech, ICML, or even NIPS. But in production, accuracy is good, it's important, but latency is also important. So we need to know, or we need to get the transcription as fast as possible. Some people say that we need to get the transcription live, like within a fraction of a second, even milliseconds. So what we have done till now, as I mentioned, we use some sort of a deep learning model here in the form of getting better context. And better context can be, we can get better context from algorithms like RNNs, LSTMs, GRUs. But what we essentially do is to get better context, not only from terms which are previous to the particular character that we want to predict, but also we go ahead of the context. And we find out that we get better context if we go like both ways. So it's important for us to have a model which is bidirectional RNN, because it's not only dependent on the words or the characters before, but also dependent on what comes after that, right? But just thinking about this, it's not possible for us to have words or characters in the future if we are doing live transcription, right? We can only do this for offline recordings. We cannot do it online, right? We cannot do it live. So we have to wait for all the audio to arrive before we can transcribe it, which we don't want to do. So what we could do is just expect our model or our CTC to delay the output and to learn on its own. And to our surprise, it does pretty well in understanding the context and then predicting what is next and taking that into account as well. But it's just not enough. So you need to do some sort of model engineering to understand what is there in future, right? So what are the solutions for this? So one of the solution is you bake more context, or you bake a limited amount of context into whatever you see. Something like this. So in our speech recognition model, we have these spectrograms, we have the recurrent neural network, but instead of having a bidirectional recurrent neural network, what we do is just have a particular context going in from ahead of it, right? So if we have to, just let's say in this example, if we have to predict L, instead of we going in greater depth and then going till the end and figuring out what we should give back or how much the recurrence should be, we only take a specific amount of context into consideration. So we only take, let's say, 1 or 2 characters or 1 or 2 time steps ahead of L to consider in our context, and we take the entire thing before that. So you bake limited context and you have that into your model structure, and this kind of works, but we again run into some other problem, which is that we want to compute these layers at the top really quickly, right? So what happens when you do this? When we are doing this, at each and every step there is this bidirectional recurrence, and because we are taking some limited context into account, we're not taking into account, or we are like giving away the time in which a particular forward RNN works. So there's another solution to that, which is move all the context you have to the top layer. So don't have any sort of bidirectional layer in the first few layers, but only have a bidirectional component in the last few layers, or only the last layer. Something like this, where you have a forward-looking RNN in your first few layers, but at the same time, you have this component of some limited context being taken into account for your final layer, right? So you are not, so in this example, when you're predicting L, you're not taking into account all the things, you're just taking into account some of the particular characters which are coming in the future, and not all of them. So this is good because you can easily recompute or even compute for the first time top layers, and you can do it even online. You can do it like live. So instead of going by this particular approach where you had context but a limited context into account, but you do it for each and every layer, instead of that, if we just squish down all the context to the top, we only have to do it once, and you can do it very easily and even online. Okay, so the summary of this talk is deep learning is basically in the first few steps, and it's gaining the state of the art in speech recognition. Actually, Geoffrey Hinton came up with using this idea of neural networks for speech recognition, and that was the wave. Many people say that neural networks came by ImageNet, which was definitely the boom of neural networks, but at the same time, you have Geoffrey Hinton doing speech recognition in like even before that. So those were the first steps, but we are definitely, we've gained some momentum, we've gained some performance in terms of data and in terms of models, but we do have to do something more. So we have to collect more and more data. We have to like come up with better models. Just to give you an idea, guys at Google and NVIDIA came up with an attention model which even surpasses the accuracies or the word error rates that we get from these kind of models like connectionist temporal classifications. So even people are going into transformers and some sort of like attention models instead of just using LSTMs and RNNs. We have to, this is really important because we have to take this into account that production is really important. Production accuracies and basically something that works well in production is really important as well. We can definitely have more research papers based on what we, based on like sophisticated models, but getting those models into production is really difficult. So we have to devise ways in which we can get the best of the existing models and also something which is production ready. And as I mentioned, there's a long way to go. We're just gaining momentum at that. So we're probably here, and there's a long way to go before we reach like the actual state of the art in speech recognition, when we say that even if there's like a lot of noise, even if people are having like different sorts of accent, we'll be able to understand what they're saying, right? So yeah, this is pretty much it. Thank you so much. And yeah, any questions? Guess we have time for a lot of questions. Yes. Yeah. Right, okay.
I just request the speaker to repeat the question for the video recording.
For sure. Okay, so that's a great question. The question is, we looked up at different models which takes into account a longer context and even take into account some context in the future, right? Instead of using recurrent neural networks or some sort of thing which takes into account this context, why don't we use a sliding window and a connet to just do the exact same thing? Great question, because people have done something similar. So there is a paper by Google I think it was in Interspeech 2015, where they used ConNets for speech recognition, and they used the exact same idea of using a sliding window detector. The only thing is, ConNets are not usually very good in understanding context. The idea of speech recognition is that context is really important. For example, if I'm saying something, that's something to identify T or H or I or N or G in that, you need to understand that some is there in the context before, right? Usually people go for recurrent neural networks, LSTMs, GRUs, or even now transformer networks. But yeah, definitely this is something that people have tried out before. But good question.
Are there any databases available, or I should say models available, that can be used for transfer learning in this space?
Right. Okay. So the question is, are there any models already available so that we can do transfer learning in the space? Yes. Talking about data sets, there are data sets like switchboard data set and even something called LibreSpeech data set, which is just people reading a particular novel, and then just, people reading a particular novel is again transcription of that novel because we have the transcription and people are reading that. So there are data sets for models specifically. Baidu has open sourced some of the models, so you can look at that. There are definitely models. I don't remember which company or which enterprise has open sourced their models, but there are models available online. If you just Google search like LibreSpeech models or pre-trained models, you can definitely do some fine-tuning and transfer learning on that. Yeah.
So what is the currently achieved accuracy for this?
Right. Okay. So the question is, what's the currently achieved accuracy for speech recognition? So I just want to mention that we do not use the term accuracy for speech recognition. Instead of that, we use a metric called word error rate, which is on a very high level just a flippant of accuracy. So the less the word error rate, the better it is. So word error rate is basically however many number of words you are inserting, deleting, and even replacing. It's like Levenstein distance or edit distance. And people have reached like superhuman levels. They've reached for switchboard corpus, which is a corpus of people speaking with southern US accents and also in a small, quiet, closed room, so very low background noise. People have achieved like single-digit word error rates to the level of making it better than even humans could understand that. So it's very competitive. I know Google's ASR and IBM Watson's automatic speech recognition models are pretty good in understanding those kinds of speeches, but if you have to have something specifically for your use case, for example, let's say healthcare or customer support or things like that, probably you'll go for something like this.
How do you integrate the language model? Do you need to compare the words with the words in the dictionary?
Can you say that again?
How do you integrate the language model? Do you need to compare the words you recognized with the words in the dictionary?
Right. Okay. So the question is, how can we include or augment language models? Do we need to increase or decrease the vocabulary or the dictionary in some way? So language models are basically included just so we have a particular set of words in our language, right? So instead of me saying ABCDE is a word, which is definitely not a word, I would say are there or something like that, which is a word, right? So language models are good because you would want to find out what is the next available character or what's the next word in sequence because they take into account the context. But to augment language models, you would just take into account a particular set of vocabulary, create a language model. You can do an n-gram language model or a recurrent neural network language model, that's absolutely fine. I know some people do n-gram language models even in production, so that works really well as well. It's just that you have to include whatever you get out of your decoder for acoustic models into a language model so that it can sort of like correct if you don't have something in your vocabulary. Does that make sense? Thanks. Good question. Okay.
Yeah. How do you handle the background noise? Is that handled like in feature engineering or in the acoustic model? Right.
So the question is, how do you handle the background noise? Do you do some feature engineering or do you specifically design models for that? I have like a two-way answer to this. One is you can devise models just to reduce background noise and then have the output of those models, which are speech signals, as inputs to speech recognition engines, right? The caveat is, if you want to do live transcription, and if you do background noise reduction, you will not be able to get live transcription. But those work pretty good. And there are studies in which people have used even convnets for background noise reduction. But at the same time, there is a hack to do this as well. If you do not care about background noise. And so the hack is that instead of you tuning this speech signals to find out like less background noise, include more background noise into your training data. So it gets more susceptible to what you want to achieve with your testing set. So one of the ways is to have, let's say if you have, I don't know, 10,000 hours of data of people speaking in a quiet room. What you can do is to add background noise in that. So now you have like 20,000 or even 50,000 hours of data with background noise, and now your models are more susceptible to background noise detection. So you don't have to go through an additional machine learning modeling step to reduce background noise. Instead, you're saying, okay, I'll just have background noise in my model, but I'll also have background noise in my training set. Does that give you an idea? Yeah.
So you kind of answered part of that, I guess, within your last answer. I guess then going back to something that you said about something, what kind of implications are there when using, say, character level RNN for resolution? And to your comment or your answer in the last case, is there anything that you might be able to do in this area to kind of fudge your training set, if you will, to introduce?
Can you repeat the first question again? I was not able to hear that.
So essentially with something, let's say, when you're detecting something within your language model, would you run into issues within, say, a character level RNN?
Yeah.
Given that something, and to your point on kind of the time window, could be picked up as 2 words or 1, I guess, given that, and how that would be handled. And would this be something, let's say, in your training set that you would be able to kind of slow down or maybe potentially fudge or play with, and just like introducing that noise, speed up or slow down the pitch of your data to kind of bootstrap some other feature? Do you get where I'm going with that, or is that a little bit too vague still?
Okay, I guess I got part of it, but I'll paraphrase the question. So on a high level, I guess the question is, if I got it correctly, that you might run into problems with RNNs. So how would you tweak your RNNs in a way that, like you mentioned, you have background noise or some amount of data which is like not ideal for this task. So I would say for character level RNNs, the good thing is that you do not run into memory leakage problems because your vocabulary is just like 30 or less characters. But the bad thing is that you might get results which are not English-like at all, right? So which do not make sense. One way to do this is augmenting language models, but there is a more sophisticated way of doing this. In addition to augmenting language models, you go through this approach of a modified beam search. So basically going in this grid fashion and then only choosing one particular character which has the best or highest probability at that particular time step. So there are ways to doing that, and I can definitely speak to you offline if you want to know about that. Sure.
Any more questions? All right. Thank
Okay.
you, Pranjal.
Thank you so much.
Thank you, everyone.